All right, everyone, welcome back. Let me begin the session by talking about the question about the zero force member. You know, I wouldn't feel good if you never asked me about the zero force member at all. So from Gavin Pope example, you know, you have something like this. Say 3 panels. It's kind of the odd one. Oops. Not like that. Right? Don't look tidy enough. So let's say whatever that is. Let's say this becomes a zero force member. Now, if I remove this panel becomes a problem because first and foremost, if you stick to your elementary assumption about the trust, you will see that the typical assumption doesn't allow this because this trust become unstable. So for typical trust, if this zero force member is removed, trust can be labeled unstable. But is that the end of the world? No. From time to time, you find out that when you go out in the real world, oh, what the heck? Why is it paused? Okay, we're back in business. So in the real world, sometimes the architects or somebody else, the mechanical engineers, would ask for your favor to remove such member. And sometimes it doesn't even have to be a zero force member. So let's say if a member is removed like that, can we have a trust that looks like this? Can we? Of course we can. This is called, spelling may be incorrect, Virendeel trust. And the Virendeel is the name of an engineer who started using stuff like this, you know. Funny how I thought it was the meaning of the structure because Virendeel means 4 sides. What kind of guy's name, you know? His last name means 4 sides. So whatever, it's like, oh, okay, we have 4 sides now. We have a rectangle in our structure. So I thought, you know, it was called because with this name because of the configuration of the truss. But no, it's a guy's name. It's a name of a Belgian engineer who started using this. But even though it's called a truss, this is no longer a truss because this, let's change the color. Oh, okay. This has to be a frame. Remember that your truss, all the joints are pinned. But when you have a case like this, this becomes a rigid joint. So even though it looks like a truss, it is now like a truss and frame put together. And
Teacher?
an analysis is impossible.
Sorry, your screen is facing.
Huh?
The screen is right.
Thank you, thank you, thank you. So okay, let's stop the share at once and do it again. Wrong button again. Yeah, it's you know, I think must be the internet. So is it back now? You guys can see it?
Yes.
Okay. So, right. So what you don't see is this one. Now you can see it. It's a Viridian trust. It's a guy's name, right? Which means 4 sides. So we have like 4 sides here. Okay. So the problem with this is that even though it is called a trust, it is no longer a trust. It is a frame. And you must design this structure such that this joint must be a rigid joint. And when you have a rigid joint, that is a frame. So it is possible to have the trust without the members, and then you can have a rectangle as a part of your trust, but it is no longer a trust. And you know, let's say if I draw a long trust like this, I believe I have mentioned quite a few times in the class that, you know, the truss is some form of a beam. Okay, and the top chord and the bottom chords are the part that take moment, right? Top and bottom chord will take the moment. Because, you know, when you look at the bending stress, My over I, the maximum stress is at the top and the bottom. So that leaves us with the webs to take care of the shear. And you will find out, like most of the time, that the diagonal member that will carry the largest force will be the ones closest to the support, because it takes a shear. And the maximum shear of a simple beam is at the support. And you can say the webs take the shear because, you know, the shear stress looks like that. Okay? It's maximum in the middle. So that means if you are going to have a case like this where you don't have the member in the middle, you better ask them to remove something closer there, right? It would be better. Now, the next issue, the weight of the truss. Certainly, when you look at one member, the weight is a uniform load. So when we start looking at the truss, seems like I have drawn so many pictures of the truss today. Whatever that is, okay? If I say, I consider the load, if weight is considered. What do you mean? What do we have here? If the weight is considered, it means that you have a uniform load all over the place like this. Uniform load is everywhere. So ladies and gentlemen, this will turn your truss into a different animal. So when you design the truss, if your members are not so big, you can say, hey, I don't want to include the weight of the truss in my analysis, and then I go ahead and calculate it. But are we living in space? The truss has no weight. No, right? We live on Earth where we have gravity. So the weight is always there, but we choose to neglect it because it doesn't affect our design that much. So you see, that is why we are engineers. We approximate everything to the degree that is acceptable. Scientists cannot do this, you know. Scientists will go crazy. How can you ignore the force? But yes, you can. So if, you know, I maybe Ajahn Anek, Ajahn Suthat, I myself, we always design the trust by hand calculation. We don't bother to use computer. It's a waste of time. Hand calculation for the trust can be done, say, no more than half an hour. You can have your trust or less. This is what you can do as well. But if you choose to use your computer analysis, let's say to get a more accurate deflection of the trust, that's fine. You may wonder how I can calculate the deflection of the trust, right? I'm not going to use VirtualWorks. I have a better method. It takes like 2 minutes to do it. Okay. But anyway, if you choose to use a computer program and you are not aware of a situation like this, computer programs generally can include the weight of the trust in its analysis. So if you don't know that the program has the uniform the weight option, and you run the analysis, and you see when you look at the results, oh goodness me, how come my trust members have bending moment? You would know that the bending moment comes from the fact that the weight of the trust has been included in the analysis. So I remember that the computer programs that I used to use had options where you can turn on or turn off the weight option. So if you turn it off, the weight of the trust is not included in your analysis, you will get the typical results, just like what Kevin Pope just shared. It's just axial force, no bending moment. But for those of you who do not know and you hate structural analysis, you don't want to do anything, so you let computer do the dirty work for you and turn the blind eye. Okay, the computer must be correct. And then you turn on the uniform load option. Then somebody look at your results and say, hey, how come your trust has bending moment? And you have no answer for that because you never care about the analysis. Then you panic. Oh, what am I doing here? Is it okay? That's the case. But there are also cases where you can use the trust to support the uniform load. It's been done. You can use the truss as the beam and say, oh, it's my, I can't stand it. Okay. You can use the truss as a beam to support the floor system as well. In that case, you truly have the uniform load that is not negligible. Let me write down for you. However, truss can also be used to support floor, which will give the true uniform load. No, not true. It's the weight is also true. Give the significant uniform load. In that case, you know, your truss will become a member that has both axial force and bending moment. And we can still design it, but you need to perform the analysis by using the computer program, because the computer program will handle this very easily. And this member will have both bending moment and axial force on it. And you guys will learn that in the second part with the Ajahn Suthat, where you can design a member that carries both these forces. Right now, you just finished the compression member with me. You are in the middle of the flexural members. In the second part, you know, you just combine them. So it's very doable. And many structures in the real world actually utilize this because sometimes the span is large, you know, to use an H-beam may be too heavy. So they decide to use a floor system like the truss to reduce the weight of the structure. So this is not uncommon. People do it, engineers do it. Okay? But you need to take care of this in a very special way. But keep in mind that these members, this member will have it bad because it will have both axial and bending moment, but it has the floor to help brace as well. So the unbraced length becomes 0, both under axial and under bending. So it's not bad, you know? All right? Is there any question? So all quiet on the Western Front. All right, can you take a minute to say maybe recharge your battery, because I would wish to talk about the angle. Would you like another short break? Because this is just the truss issue, so it would not be a bad idea to stop the session and we have a video exclusive for the truss, and then we have another video exclusive for the angle. Or you would want to continue? Hey, hello.
Short break. Short break.
Short break is good. Okay, so let's have a short break.